All right, let's jump right in. Welcome to The Explainer. Today, we're tackling the two absolute biggest headaches of scaling large language models: skyrocketing costs and lagging latency. If you are building AI applications today, you know exactly what I'm talking about. Here is our roadmap for today. We'll start with the LLM cost problem, introduce prompt caching, and compare it to conventional caching. Then we'll break down exactly how it works, look at some real-world AI use cases, and wrap up with the limitations and key caveats. So, Section 1. The LLM cost problem. Let's start with the primary pain points of building AI applications right now.
I want you to imagine for a second sending the exact same massive document, let's say a 50-page company policy, to an LLM over and over and over again. Every single time a user asks a question, the model reads the entire document completely from scratch. Just think about what that kind of redundant computation does to a system when you're trying to scale.
Well, there are two major challenges here. First up, every single token processed incurs a charge. So, with redundant computations, you are literally paying to read the same text 1,000 times over. And second, latency. Processing those massive requests takes time, which seriously degrades your app's responsiveness and just leads to an incredibly subpar user experience. Moving to Section 2. Enter prompt caching. Let's look at the hero of our story here. Prompt caching is a remarkably straightforward way to boost both speed and cost efficiency. It basically works by storing the frequently unchanged parts of a prompt, like your system instructions or really heavy reference material, so the model just avoids reprocessing identical tokens. Think of it like leaving a bookmark in a massive textbook. Instead of reading the whole book from page 1 every single time you need to find one specific detail, the AI just flips right to the bookmark and only reads the new stuff. Pretty clever, right? Now, Section 3. Prompt versus conventional caching. You might be sitting there thinking, wait, isn't caching kind of an old concept? Let's see how this actually builds upon traditional methods. If we look at their primary goals, they definitely serve very different masters. Conventional caching is something we've used for decades, to store frequently accessed data like HTML pages, database queries, or images. It lowers back-end load. Prompt caching, on the other hand, specifically targets the LLM token bottleneck. Its entire goal is to save repeated LLM prompts to avoid expensive recomputations and drastically reduce that latency. So, a really crucial point here is output reliability. With conventional caching, it's deterministic, meaning the same database query always produces the exact same output. But with prompt caching, it often requires a precise match, not just of the prompt text, but of the model parameters too. Things like temperature or top P, those have to remain exactly the same for every request to trigger that cache hit. And that brilliantly illustrates another key difference: expiration. Conventional caching is typically managed via a simple time-to-live or TTL, or maybe you do some manual invalidation when your database changes. But prompt caching is deeply tied to the model's actual lifecycle. Expiration here is often linked directly to model version updates or retraining cycles. It's really a completely different paradigm. All right, Section 4. How prompt caching works. Let's slow down for a second and break down the actual mechanics of how this happens under the hood. There's a 5-step lifecycle at play here. First is key generation. When a prompt is submitted, the system creates a cache key. What's really fascinating is that this can be an exact match cache using the literal text and parameters, or it can be semantic caching, generating an embedding to find semantically similar entries. That means you can reuse a cache even if a user slightly tweaks their wording. Step 2 is the cache lookup against your store or vector database. Step 3, you either get a hit or miss. A hit returns the stored result instantly, bypassing the LLM entirely. Step 4, if it's a miss, the LLM processes it and we store that brand new result for next time. And finally, Step 5 is invalidation, where entries expire to make sure answers stay accurate and timely. Now, you might be wondering, how much work does this actually take to implement? Well, the good news is you don't have to build this entire pipeline from scratch. Frameworks like LangChain offer incredibly flexible, out-of-the-box implementations. They bring prompt caching together with other components like memory, tool integration, and retrieval-augmented generation, or RAG, directly into your LLM applications. Moving on to Section 5, Real-World AI Use Cases. Let's inject some energy here and look at why this absolutely matters for your business. If you're building interactive documentation portals for internal knowledge, caching standard organizational procedures gives your employees instant answers without querying the LLM every single time. Or consider marketing campaigns during peak traffic.
Pre-computing answers for common queries about discounts or product specs easily handles the surge in load. And in customer support systems, caching troubleshooting steps or billing explanations ensures faster, perfectly consistent responses, completely avoiding unnecessary LLM calls when user traffic is through the roof.
The sheer advantage here is just massive. It provides infinite capacity, consistent responses, and intelligent resource usage. You are dramatically cutting those API costs we talked about at the very beginning, while simultaneously supercharging the user experience. You're essentially reserving your actual, heavy compute resources for the complex, varied queries that really need them.
Finally, Section 6, Limitations and Key Caveats. To ensure an objective analysis in this explainer, we really need a reality check. When might this tool actually get in your way?
Because prompt caching isn't a silver bullet, right? If a user query needs highly dynamic, real-time data or involves a context-sensitive multi-turn conversation, a cached response might give users stale or completely irrelevant information. You also introduce added complexity for handling edge cases, like trying to support partial prompt reuse. Plus, there is real operational overhead in managing cache expiration settings and storage constraints. You always have to balance the speed with the need for accurate up-to-the-second data.
All of this leads us to a critical question. How will you balance AI scaling with cost efficiency in your pipelines? I want to leave you with this final provocative thought. Take a hard look at your own AI architecture. Where are your models doing redundant work? Where could a simple bookmark save you thousands of dollars and milliseconds of latency? Challenge your assumptions about how your LLMs are processing data today. Thanks for joining me on this explainer, and I'll catch you on the next deep dive.